Hello everyone, welcome to this 10th video on power spectral density. We are dealing with problems in linear power spectrum and given an input power spectral density, how to convert it into an output power spectral density using your system transfer function. The problem is a circuit has an unit impulse response given by h of t is 1 by t, 0 less than t, greater than or less than or equal to capital T, and it is going to be 0 elsewhere. We'll have to evaluate syy of omega in terms of sxx of omega. Now what happens over here is we have been given with an output power spectral density, and what we want being given is we'll have to estimate this in terms of my input power spectral density. Now x is going to be the input, it is going to be processed and it is going to produce an output. This processor is going to be our capital H of omega, so that we have by the theorem syy of omega is modulus of h of omega the whole square sxx of omega. In the last problem we had two parts where we computed capital H of omega from our small h of t, which was the Fourier of it, and we had the autocorrelation function given to us using the Fourier of it. We computed the power spectral density. But now in this problem we have been given only one part, so I have only this part. This part doesn't exist, so the problem becomes half of the original problem. Now this second part can be directly stated using this formula. So my task now is to just evaluate what is going to be my capital H of omega. We need to recollect that capital H of omega is nothing but Fourier transform of my small h of t. And what is going to be the formula for Fourier? Integral from minus infinity to infinity h of t e power minus I omega t dt. Now what is going to be the limit which has been given to us? The limit is going to be from 0 to t, and the input is going to be 1 by t e power minus I omega t into dt. This 1 by t is going to be a constant, so let me pull it outside. E power minus I omega t on integration with respect to the variable t gives you e power minus I omega t divided by I omega. Now apply the limit between 0 to t. Now what happens in our next slide? You apply the limit 1 by t. When you take the upper limit, e power minus I omega small t becomes capital T divided by minus I omega. Lower limit becomes e power minus I omega of 0 divided by minus I omega. So now this can be rewritten as minus of minus makes it as plus, so this becomes the first term. E power 0 makes it as 1, so I have 1 divided by I omega, minus sign is here, e power minus I omega t divided by I omega. Let us take the LCM common outside. E power I omega times capital T, 1 minus e power minus I omega t. Now the signals are best evaluated in terms of trigonometric functions, so we will try to convert this exponential function as a trigonometric equivalent. So what will I have over here is, I need to keep in mind that the formula e power minus I theta is going to be cos theta minus I sin theta. So this is going to be the formula which we are going to apply over here. So now what happens for the function? In place of theta I have omega t, so this becomes cos omega t, minus sign is here, minus of minus makes it as plus I sin omega t. So this becomes my next step. Now I further need to simplify it, so I will be making use of two trigonometric identities one more time, where I replace 1 minus cos theta to be equal to 2 sin square theta by 2, and my sin theta can be rewritten as 2 sin theta by 2 cos theta by 2. So now replacing these quantities in the original function, I have it as 1 by I omega t. So now I replace it as 2 sin square, in place of theta omega t divided by 2 plus I times 2 sin omega t divided by 2 cos of omega t divided by 2. So this is the replacement for 1 minus cos theta, and this is my replacement for sin theta. So my common term that can be pulled outside is 2 can be taken outside, as well as and sin omega t by 2 can be taken outside. So let me take a 2 sin omega t divided by 2 outside. So I will be left out with sine omega t divided by 2 for my first term. That has come outside. One of the sine has come outside and 2 has come outside, sine has come outside, I is still here and cos is still there. So plus I cos omega t divided by 2. So this is what I have, and in the denominator I have I omega t. Now this I in the denominator can be taken to the numerator as minus I, because I square is going to be minus 1. So let me take it to the numerator as minus I 2 sine omega t divided by 2 divided by omega t. Now what we are going to do is pull this I inside so that our term now gets replaced as 2 sine omega t divided by 2 divided by omega t. This minus I gets inside, so minus I sine omega t divided by 2, and this I you have to multiply I with minus I, so it becomes minus I square. You know I square is minus 1, so minus of minus 1, this becomes plus cos omega t divided by 2. So now this is of the format cos theta minus I sin theta. So finally we have our capital H of omega to be equal to 2 sine omega t divided by 2 divided by omega t into cos omega t divided by 2 minus I sin omega t divided by 2. So these are merely a conversion of your exponential function to a trigonometric form, which is more suitable for the transmission of signal. Now we have computed our h of omega. Move on to check what is our target. I want modulus of h of omega and then square of the term. So what we are going to do in the next stage is consider modulus of h of omega. So this becomes modulus of 2 sine omega t divided by 2 by omega t, the real part that will not be affected. But what gets affected over here is the complex number cos of omega t divided by 2 minus I sine omega t divided by 2. Now we know that modulus of cos complex number is nothing but root over real part square plus imaginary part square. So it becomes sine square omega t divided by 2. So this is going to be my equivalent of modulus of the data. Now you have it of the format and you have your 2 sine square omega t divided by 2 by omega t as such. Okay, so what is going to be the identity now? Cos square theta plus sine square theta. Cos square theta plus sine square theta is going to be equal to 1. So now this part turns out as square root of 1. Square root of 1 is going to be equal to 1. So we just have modulus of h of omega to be equal to 2 sine square omega t by 2 divided by omega t. But the requirement is modulus of h of omega the whole square. So square the data. So in which case you will have modulus of 2 sine omega t by 2 divided by omega t the whole square. So now this is going to give me 4 sine square omega t by 2 divided by omega square t square. Now we are ready to put it back in our final stage. What we want is sy y of omega. This can be expressed as a function of the input power spectral in terms of this h of omega. So make it as 4 sine square omega t divided by 2 by omega square t square into sxx of omega. So this completes the problem. We need to keep in mind that this portion is what plays the role over here. We are not evaluating this part because we don't have an autocorrelation function given. So we just express the output power spectral in terms of the input power spectral. That's it. Thank you.